Hey all, welcome to this video. Today we're going to take another look at frequency response analysis. Can't wait. This will be the second of two videos for direct or modal frequency response analysis. And just to start things off, I will show you the tutorial I'm following here. So in the last video, we covered the direct frequency response analysis of a flat plate. And in this video, we will instead use this modal approach. And just to quickly show the difference between the two, let's reconsider the help page I also showed in the last video. So let's dive on that a little bit because it's important to understand those two different concepts. So we have direct frequency response analysis, which solves complex algebra to get what we want. And we have the modal frequency response analysis, which uses shape modes. Right. Now, what I just read through those two paragraphs again, and so the direct method is more efficient for models when you have a very high frequency of oscillation. Maybe just to cut back a little bit on that. Frequency response analysis is the analysis of a structure responding to a sinusodial excitation. So that's what it is. Now, this direct method, now let's say you have an excitation on this point on a structure, which is very high. So this would need the modal frequency response analysis to extract a large number of modes in order to reach that frequency, or to get a mode which is in this frequency range. So there, the direct frequency response analysis might be a better choice, but important, modal frequency response analysis is generally more efficient than the direct frequency response analysis for larger models, right? So here, depending on number of modes computed and retained, reduce the problem size. Both of these factors tend to make the modal frequency response analysis computationally more efficient than direct frequency response analysis. It is used for large models where a large number of solution frequencies are specified. This method replaces the physical degrees of freedom with a number of modal degrees of freedom. Yeah. All right. So just that we have those two differences set clear. So yeah. Hope that left you not confused more than it should. I just want to point out another page I found in the OptiStruct help, which is pretty cool. It's on the frequency response analysis. And here you can read through all the theory behind it a little bit, like also in that help page. But in that term, I find it a little bit more easy to read, to be fair. And yeah, so I won't go through here, but you have here the sinusoidal excitation of the structure, and you want the response of the structure. You see that here with the blue line being the excitation curve, and the response of the structure could be anything, and it's displayed here in the orange curve. Yeah, so just I want to point that out. So this page exists, and if you want to dive a little bit deeper into the theory, you are welcome to do that. Yeah, and I think this page helps. Also, it goes a little bit beyond the frequency response analysis we're doing in this tutorial. All right, I will quit now the introductory talk, and we'll start with the tutorial. Let me quickly get my model here, which is the same model like in the last video. So it's not really a difference. It has the same number of nodes, same structure, same p-shell, as far as I can tell. And so this should be pretty familiar, but we will do it either way again. And hopefully solve some issues, because I was able to solve some issues I wasn't able on the last video. So this will be exciting. All right, so let's go into here. So I just quickly import the FEM model like the tutorial tells you to. And then, no, we don't want to use panels. No panels for me this time. Now you can see again, you have the plate here, and the first thing you want to get is the node IDs, and the node IDs are retrieved by just selecting the nodes selector by pressing N. selecting all the nodes and hitting the letter Q, which just shows you the element numbers. Now, you want to create load collectors, and if you don't have a load collector browser open, you can just simply go into the Modal browser and create load collectors from here. That's easy as that. So I will not follow the the tutorial one-to-one, but more or less. So yeah, I will cut a few corners. All right, so no card image. I will create a load collector called SPC. Yeah, multiple. And yeah, go into the load collector browser. You can see now SPCs is the selected and main collector. So I can just simply go ahead and create the loads already, or the SPCs in that case. So just making sure that's the same side here. So the 532, that's correct. So I go here into analysis and to BCs. Always click that, I don't know why. Then on constraints, and then my panel opens, and I will shift myself a little bit up. Now, I will just select those nodes and everything but the 6th degree of freedom. Been practicing, no. Create that. So what that does is it holds the structure in place in every direction but the 6th degree of freedom. So this is what is done here. Then I created another load collector because we now want to create a unit load. And this unit load, I want to have some value for DOF3, but in this case I will not use the SPC, but the D area. Again, this is used as the unit load being excited by the oscillation function. We will see in a bit. But I think in opposite to the first video with the direct frequency response analysis, the modal response analysis requires you here to put in a value of 1 rather than 20. Not really sure if that's, I think that's a difference just in the tutorial files. You would not be required to do that. So this change that changes the amplitude, I guess. Yeah. Now I will create that on this node, I think. No, wrong, on this node. By the way, deselecting with shift. That's new. Yeah, so I have that one. So this is set, stuff 3D area. This is all good. Now, we want to create the frequency range table. So this is just a table D with values where you can just sweep through the frequencies. And this will be just a constant value of 1, starting from 0, going to 1000. So this is just it. All right, model, create curve. Now you get that huge curve editor. To shrink that down, that you can see that too. All right, I will just call that table D, but make no mistake. Right now, this is not a table D. So we have table and property editor. Okay, I would like to create some values here. Not really sure why I cannot do that. Press tab. Oh, there's an error. Okay. Let's see. I will close that, go into the curves. Yeah, you see that? It's not table D1, it's table DMP1, which is something used for damping, I guess, because DMP. Table D1, so this is set, and now the load collector, the curve is disappearing because it's not longer a table D, table DMP. Yeah. Let's edit it right here. Okay, I can edit a value here. Can you see that? Yeah, you can. So I will do that just here. So 0 and 1 and 1001. So this is the curve. Pretty straightforward. You can see it also here, but it's not really that difficult to imagine, I think. So we have done that. Now we create load step import for the rload2. And just to give you a little hint on that one too. The rload2 in the help, you can find that here. So this defines a frequency-dependent dynamic load, but the load, the actual load, is with the d area constraint of the form P depending on F, A times B depending on F, and this is E to the power of, just a frequency in a complex space for use in frequency response problems. So can be used when a frequency-dependent dynamic load input is available in magnitude phase number format. The other one would be real and complex, I think, which is called RLOAD1. Yeah, this is a real imaginary number format. And we're using, sorry about that, we're using RLOAD2 in our problem here. All right, so now let's go ahead and create that. And this would be a load step input. So right click in the model browser and create load step input. And then there should be something like frequency dependent dynamic load. Yeah, this is the one. We have RLOAD2 here. So excited, this is the constraint we want to excite here. And this would be the unit load. Okay, this is set. And now the TBLD option, you could use TB. I'm always getting confused about this too, but TP is time dependent, I hope. Yeah, not 100% sure here. I could quickly get that, but I think it's time dependent. The other one is frequency dependent, but no, that could not be, because dynamic load frequency, it's frequency dependent, but TP, I think this is, I have to look it up. Sorry about that. So it's RLOAD2 and TP. So TB, what does it say in the help? Yeah, so TP gives phi depending on F in degrees. And the other one gives B depending on F. So it's just a difference on how you give the table, how the table should be interpreted. So if you just check back here, you can see here this B depending on F. So for TB, you set really the B depending on F value. And for TP, you have the phi. So this should be the phase, which is this one here. Yeah. Maybe there's another thing in the load and the comments here. I think I read that a little bit in more detail on another page. I cannot find it right now, so I will maybe look that up and write it into the comments. Right, but we use TB here, pretty sure. TB, yeah. Okay, so let's go back into the tutorial. So TB is here. So I will select the curve. We have just one curve here, and we will choose that one. Okay. So, and we just call that RLOAD2, that we can find it again in the load step inputs later on. Now we need a frequency collector to just define an array of frequencies for which we calculate the load response in later on. So let's do that. This should be a load collector. So create load collector. And we will call that load collector frequency 1. Yeah, because that's what we're using here. Same thing as in the direct frequency response. So we will use frequency 1. Frequency 1. And we should use a lower frequency of 20. The delta frequency should also be 20. And we want to use 49 steps of increments. And I think that's about it. All right. Now comes the difference. On the direct method, we would be set here, but on the modal method, we would want to have another load step input for the calculation of the eigenvalues. And this is the, I always don't know how to pronounce it, eigen load collector. Yeah, so you know what I mean. So it's the real eigenvalue load step input. So name, again, a friendly name. And the color, I don't care about the color. For config set, real eigenvalue extraction. So this is that. Yeah, that's okay. Type eigen should be okay. V1 should be 0. So this is a low frequency to respect. And V2 should be 1,000, I guess, because we want to calculate until 1,000. So this should be 1,000. So frequency range 0 to 1,000, and in those ranges, the eigen value analysis is done. And it's using the Lanchos, I think it's Lanchos method, which I would have to dig a little bit deeper if I would like to cover that here. But just that you know, it's the Lanchos method. Okay, all right, so this is done. And now we can create the load step. And the load step is now a frequency response, but in this case, modal, right? So it's that one. And now it comes the game again. So SPC, that's fair. Then deload, that's also clear. That's the rload, which is itself pointing to this constraint here. And then I think we have for sure the method add the frequency collector. And then I think it's method struct. Let me see. Yeah, method struct is the eigen load collector. So let's assign that here. All right, that's it for the load step. So everything is set up. And now we come to the part where I had a little bit of a problem last time with the set creation. And it happens to be the case that the card image none does not work. Not sure why, to be honest, but we had that problem, and I will show that to you, just that you know what I mean, or what I'm talking about. I will move myself up a little. So we want to create a set. Why should we create the set? We want to use the set for a output request, because we want to have the frequency response over the frequency for different kind of nodes, and not all of them, but we want this one, and this one. So 3 nodes, and for that we would need to create a set. So let's create a set. And as the tutorial tells you to do, is to use no card image here. Non-ordered will not work really. Well, I don't know really, but you have to make this dirty trick to get it to nodes. So this is a bit strange. But if you do it like that, let me tell you what happens. So if you just choose those 3 nodes, this would be set 1. So those nodes are assigned. It's a node set. And if you just look at it, I would not think that it's any difficult, because it has nodes, it has non-ordered, it has 3 nodes, should be fine, right? But let's create another one, and I use set 2 here, just to save some time here. And we will use set 1, but I'm not really sure why. Set 1 or set 3, I just checked the help. They're just saying that it's regular node sets, grid sets, so I really don't know the difference. But set 1 worked, and that's really the only I checked. So set 1, and then I just select the same nodes again. All right, so we have now 2 sets. Why isn't it appearing here? Let's see, let's check here. Model. Okay, so sets has now 2, and one is somehow a collector, and one has this defined card set 1. So now let's see what happens. So I have both done here. Tutorial says do it like the set 1, and I have found out that set 1 as a card image worked where the other one did not. So why? We'll see. Now we want to create this global output request for this set we have just now created. And this is done with the control cards. You can go to the control cards here, or also in the panels. That's also something which works. Now global output request is on the second page, so you have to click next once, and then you have it here. global request output. Now, you want to have the displacement. So you have to click down here to go to node damage displacement. Now the thing, what we want to do is we want for a form, we want to have the phase. And I don't know why this did not work. Phase. Now we travel over to the right. And the option, it's not all, we want to have a set ID. Now we have to move again. And now we have this set ID collector. And if we just click double here, then we can select one of the two sets. Now let's let's look and see what happens here on the bottom left. If I click here, wrong entity, select in ID group, whatever, it doesn't work. Let's do that again for set 2. That worked, and you can see the ID. Oh, now I'm in the way again, right? Let me just quickly hide myself here. All right. Oh, and you can see my OBS. I'm sorry about that. Yeah, you can see the ID here, right? And this is, yeah, proof that it works. All right, I'll get myself back here. And this is the one thing I could solve in this tutorial. And I think it should work the same way in the other tutorial as well. So it's just a matter of problematic set creation or set pointer, I think. But I'm not really entirely sure what the reason behind it is. But this is a workaround, so if you have the same problem, just use card image set1. All right. Yeah, so let's just continue. We have now set the global output request for displacement, but we want something different as well, I think. No? Yeah, no. So displacement is enough for us. I thought we had something here, but no, this is another control card. We now go to the next page, and then there's param, and here we want to have multiple things. So I will go through them once again. It's the same thing as in the other tutorial as well, and I will not explain it in detail, so if you want to check what they are meaning beyond what I will tell you in one sentence, then you are welcome to check the other video for the direct response analysis. Now the first thing is cup mv1. So let's go down. Cup mass. This should be set to yes. So this is using the coupled mass approach and not the lumped mass approach. Then we go to the structural damping parameter, which is the G, and set this factor to be 0.06. And then we have the weight mass, which converts mass to weight units. This should be 0.00259, which is the value for steel, by the way. Yeah, so this is done. Done. Okay, now we can return. So global output request is set, param is set, and then we should also do something with the output. No, not the out file, sorry. If you ever have clicked that and you want to have that green go away again, it doesn't really matter usually, but you can delete and then click the card, then it's gone. Okay, now output, it's up here, and we want to have, in this case, even more than in the last video. We want to have 3 output requests here, or output files, I should say. So I don't know if the order is important, but I don't think so. But it's telling me to exactly use the first to be the HG frequency, which is the hypergraph frequency, and we want to have all. And the next one should be the opti, and the opti is ASCII readable file, so you can open that with a text editor of the displacement in that case. Things, and it should be the displacement here. But you can use, I think you can use that also for objectives and stuff like that. But yeah, don't call me out on that. Now the third one should be the H3D. So this is a standard output, and we will also use all for here. Yeah, really? No. Okay, I will go for it. And I will leave that empty, I think. Yeah. Okay, now we have set everything up. And because I was able to create that set in the right way, and we should be able to run that. And also have valid results for it. So let's see about that. I will just run it and hope I don't get any errors. It does not run. Permission denied. Okay, maybe I will just use another suffix. Okay. Okay, that looks good. Now I will click on results to open the hyperview. And this time I will be able to also set up the results properly. So we could look into the files, but I think that's the same thing as in the last time. So you have the out file, you have the H3D file, you have the REST file, you have the HTML file, you have the disp file. This is the opti output to check for the displacement values. But what you really want to do here is to see those frequency plots. So where you have the frequency at the x-axis and you have the magnitude of the displacement in the y-axis. And then you can just see where are the problematic frequencies lie, where you have this excitation multiply the displacement. All right, so how to do that? First off, let's open the frequency.mvw. So this is a session, and I think I should not open that here, but open it here. To a session. Yeah. So I will just confirm it here with yes. So I could look now at the shape and modes and stuff like that, but I don't really want that right now, but I want to have that plots. And you can see here that you have 3 of those plots, which correspond to the 3 nodes in your set, which is exactly what we want. And the only thing the tutorial requires you to do, or yeah, rather it's a suggestion that you should do that, is to just go into the axis option and go to scale and ticks and put that into logarithmic, because that's just, yeah, so the way you do it here. So you can see the frequencies and you can see exactly that's the same thing as you would have here. Yeah, so I got my window bar appearing. Yeah, so this is exactly what you have here. So, and yeah, again, the comment that the disp file contains the displacements of those 3 nodes in translational and also rotational degrees of freedom. Yeah, so this is about it. Just if you would want to, yeah, cycle through them, you can with the arrows up here. So that's one way to go through those plots. Maybe you have to change the axis for each one. That could be, because that's not logarithmic. Yeah, but that's more or less it. So you have phase and displacement, magnitude, output for the frequency analysis, and this should give you a good hint on what problematic frequencies exist in your model. So it was a fun tour until now for me to go into this frequency domain, which is not really my everyday go-to thing. But I will continue to do so and just also go into random excitation, not just sinusoidal, I think. Yeah. Yeah, to just use also random things here, and also maybe a little bit on transient dynamic analysis. So this should be fun for the next few weeks or so. Let's see. So yeah, if you like the video, please like, subscribe. Let me know what you think, what you have experienced in that domain. Yeah, if you have any questions, comments regarding those kind of analysis, just let me know in the comments. And yeah, so if you just have anything, write me a mail. All right, bye guys.